All right. Good afternoon, everyone. So this isn't the last talk. There's another talk at 6 p.m. So do come back for that. But this is the last of SLT high numerically. So SLT high 4 is today. SLT high 3 will happen sometime next week. That's why there's a skip in the number. Okay, but this is like logically, thematically the conclusion. So just to remind you, in SLT high 1, we saw that the free energy formula and internal model selection give us a powerful tool for studying phases and phase transitions in the Bayesian posterior. And actually a few questions came up then and subsequently about how this relates to what we see when we actually train networks, right? So we're looking at a network trained by SGD. There's a drop in the loss. Maybe that drop is repeated over many different runs, so it seems to not be something accidental, and structure emerges during such a drop. So it's tempting to call that a phase transition. Is that a legitimate thing to do or not? So I'll go through that as clearly as I am able. Yeah. If we can succeed in relating phase transitions that people observe when structure forms, and we've gone through a couple of those in the context of the mechanistic interpretability talks, if we're able to link that structure formation to phase transitions in the Bayesian posterior, and as we discussed over the course of this week, we have a pretty clear idea of how phase transitions in the Bayesian posterior relate to differential topology and algebraic geometry. So if that through line succeeds, then potentially we have a very interesting mathematical language to talk about the structure that's formed in those phase transitions. Now, we don't know that that through line actually does succeed, but I'm going to explain some reason to think it's not fanciful in the context of the toy models of superposition example, which I'll say a bit about in a moment. Okay. So I'm going to present some of this as work in progress with Susan Wei and Edmund Lau. Susan will be here next week. Edmund, of course, you've seen already. It's work in progress, and many of the questions you might ask about this I won't be able to answer, but I'll present what we know so far. Perhaps the main takeaway from this talk is that this toy model, which Ben introduced, is not only an excellent test bed for looking at superposition, but an amazing example for SLT. Completely, I mean, independent of any connection between those two things. This would be a great example for people to study in the context of SLT. It is not easy to find great examples where there are just lots of phase transitions laying around, and this is one of them. So the references, the toy models of superposition paper, El Hage et al. The second paper, which I'll call Toy Models 2, Hennigan et al. Superposition, Memorization, and Double Descent. I'm not going to say too much about that, but maybe it'll come up in questions. And I'll just remark in passing, I originally planned to say more about tight frames. There was some speculation in the original Toy Models of Superposition paper that what they're observing is connected to the Thomson problem. As far as I can tell, that's an analogy, but mathematically it's not that directly connected to the Thomson problem. It is, however, quite close to what are called tight frames, another very deep, interesting area of optimization theory. So take a look at this paper, you'll see a lot of parallels. And for anybody wanting to go much further in, say, classifying the local minima of what I'll call in a moment the toy models potential, this will be a good resource to pick up the right techniques. And to be clear, the toy model's potential that governs superposition in this example is not, as far as I can tell, already existing in this literature. It's like a variation of that problem, an interesting one. So here's the problem. We're going to consider mapping L linearly independent features into M dimensions, and then attempting to recover them as well as we can with L greater than M. I'll start off by talking about sparsity. Ben already presented this briefly. We're going to take the high sparsity limit for the rest of the talk, but just to motivate that briefly. So this is just a formula which says, as Ben explained, take a L-dimensional, so produce an L-dimensional vector, excuse me. Produce an L-dimensional vector by sampling a subset of dimensions which get to be non-zero, and then uniformly sampling each of those coordinates. That's what that says. The high sparsity limit is uniform. Right? If you just look at this expression, if you take T to be empty, that is, you didn't select any coordinates from which to sample from the uniform distribution, you just get the zero vector. As you take S very large, everything else is suppressed. Right? Sorry, not uniform, it's a Dirac distribution at zero. So that isn't what you really mean by the high sparsity limit, right? So by high sparsity, what I'm going to mean is the next order term, where you're basically only ever going to see a vector that is in one dimension, right? So pick a direction and then sample the length of that unit vector uniformly from 0, 1. So that's what we're going to mean by the true distribution in this talk. It's what we mean by the high sparsity limit. The follow-up paper that I mentioned earlier, Toy Models 2, is doing something quite similar. Okay, so that's our true distribution. We're going to now describe the model. This is as it was in SLT high 1. The model is as it was there, but fxw is now a particular network. So the notation here, there's going to be quite a bit of notation in this talk. Lowercase w, the weight, is made up of two parts. The weight matrix W, capital W, which is M by L. Right? It's mapping features in L dimensions into M dimensions. Curly W is going to mean parameter space. B is a bias vector. My biases are always non-negative. This is just, it makes the algebra simpler, and in practice, when you're training, you don't see positive biases. Okay, the bias is not playing a very important role.
Did you say no negative bias?
I did, non-positive, or what? Yeah, not strictly positive, less than or equal to 0. Okay, so the model takes an input X, a weight vector W, comma B, and outputs ReLU WTWX plus B. We're just taking this as given. I'm not going to motivate why this is a good model of superposition here. The EIs are the standard basis in RL. Given W, we're going to write W1 through WL for the columns and B1 through BL for the entries of the bias. Okay, so the toy model's potential is just the KL divergence or average negative log likelihood up to some constants that we don't care about. It's just this mean squared error. The reconstruction error, right? So this is the function we're interested in on the space of pairs consisting of a matrix and a bias. And we're going to call this either the toy model's superposition potential or the toy model's potential. So here's what happens when you train a gradient descent trajectory on this potential. We saw pictures like this in Ben's talk. So you can kind of ignore the bottom panel here. These are histograms of magnitudes, norms of the columns of W and of the bias. Probably also don't care about that too much. Focus on this. So this shows you the training loss over the course of training. The red dots are at that point in training, the weight matrix is taken out and its columns visualized. So each arrow in the first row is a column of the matrix. So you can see here that at this point in training, 2 out of 5, I apologize, that should be an L. I had to change notation because I didn't want to clash with the N number of samples. Okay, so I hope that's, well, it's not going to be the only place. So we're mapping into 2 dimensions. We're trying to represent features in 2 dimensions, and we have 5 of them. Here, 3 are unrepresented and 2 are represented, and they're put in opposing as an opposing pair. What the original paper calls a diagonal. And you can see that over the course of training, the loss drops, seems to settle on a new plateau. And that plateau is characterized by embedding 3 features rather than 2. And then you see something interesting happen between pictures 3 and 4, right? One of the unrepresented features starts to grow and becomes represented, and then you have a foregone. And you see that there's something like 3 level sets here corresponding to the digon, the 3-gon, and the foregone. Okay, so that's quite interesting. Yeah.
What's the
green line in the loss?
Oh, that's LN.
Okay.
Yeah, so this is, I mean, basically this is the empirical version of the green line. N is much larger than the number that's used to calculate the training loss. Here's another one, perhaps much clearer. Plateaus, basically the same kind of trajectory, right? You don't actually see the 3-gon because the sample was taken somehow halfway between the 3-gon plateau and the 4-gon, and you can see that that is consistent with the way the weights look. These red lines down here are an empirical estimate of the learning coefficient. The numbers on the right-hand side, you'll notice, don't make any sense. But what's important here is that this quantity, which is, we're going to say later, associated to the phase, diverges at the phase transition. So that's another interesting feature. This is the final one I'm going to show, and it shows a transition from something that looks like it used to be briefly a moment ago, a 4-gon, and then is becoming a 5-gon. Okay, so that's what just stares at you as soon as you start playing with this example. So let's ask some questions. Are these level sets phases, in the sense we've been defining phases in the Bayesian sense? If so, then they're associated to some singularity. It would be natural to conjecture, given the pictures we've looked at, that the singularity is the k-gon, right? 2-gon, 3-gon, 4-gon, 5-gon. Is the change, say, from the 4-gon to a 5-gon a phase transition in some sense? Right? It's clearly like a phase transition in the sense of, look at the loss plot, loss goes down quickly. But can we put like some kind of stronger argument behind the idea that that's a phase transition? Both in the Bayesian sense and maybe also in some other sense. This is something that also came up, I think, yesterday. So we've talked about, in physics 4, I think. So we've talked about phase transitions as sudden changes in the Bayesian posterior, or in physics 4, a sudden change of the equilibrium state to a different minima. And under the Maxwell convention, that was just like a teleportation, right? State over here, state over there. There was no story about how it moved from one equilibrium state to another. That is, there's no mechanism for how the system actually achieves that change in its structure. Okay, so but we might be interested, given we can look inside this model and maybe write down some equations if we can give a story about what this phase transition actually is mechanistically. And having done that, maybe we can say something about the relation between these two kinds of ideas of a phase transition. On the one hand, the phase transitions in the Bayesian posterior, which I hope you agree are now mathematically on solid ground, and the phase transitions in SGD steps, which I would say really are phase transitions. There's nothing wrong with using this language. It just remains to be proven in each case that it's legitimate. But I think people are totally on solid ground using this. Eye candy. Okay, so phase transitions in N. This is M equals 2. Again, forgive me for the labeling. It's L equals 5, so 5 features in 2 dimensions. And what we're seeing here, the y-axis is the proportion of k-gons. K is ranging over 3, 4, and 5. So 3-gons, 4-gons, 5-gons, the ones you saw in those plots earlier. So at any given n is the x-axis here, at any given number of samples, we can look at the Bayesian posterior. It's concentrated in some parts of the weight space. And we just need to decide a way of saying which weights correspond to 3-gons, 4-gons, and 5-gons, 6-gons, 2-gons, 7-gons, etc. Okay, so here's how we do that. just to find a function which takes the weight matrix and counts the number of vertices in the convex hull of the vectors that are the columns. Well, Edmund wrote the code, so he should correct me if I say this wrong. Okay, so that's an integer. And then I just take the pre-image, right? So the Kagon phase is just this region of weight space. Now, of course, some of those are like halfway between, it would seem to us, a 3-gon and a 4-gon, right? So these are not like platonic Kagons. That's not the point of the phase. Okay. Note that at least if you follow the logic of SLT high 1, where we took this partition of unity, blah, 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 then the probability that you are in one of these regions that's classified as a Kagon, that is FW equals K, is proportional to an exponential of the free energy, right? So this is just getting, it was basically the same kind of thing in Liam's talk, right? Plotting the free energy directly is one way of trying to look at a phase transition, but it's equivalent to plot the concentration of probability in some region of the posterior. Yeah.
Could you collapse the pictures of everyone else in the
Oh.
table so that I can see your slide a bit better?
Yeah, thanks. I'll try. I can't see my mouse there.
Maybe it might not be worth that.
Yeah, I don't know.
You have to exit the.
I think that's okay. Yeah, I agree. It's distracting, isn't it? Yeah, thank you.
Shouldn't have to. I guess different things, actually.
Someone
No.
There's
One.
All right.
Yeah, there.
Group F. All right.
Yes.
Very good. Yeah, so another way of looking at it is just to plot those probabilities, because up to a negative logarithm, that's the same as plotting the free energy. So having a crossing line of free energies will be the same thing, assuming that as a crossing line here. But it's of course around the other way, right? So higher probability will mean lower free energy. So if you're thinking about the phase, you want to be at the lower envelope of the free energy curve. That's the dominant phase. Of course, you're at the higher probability envelope on this curve. So for low n, the 4-gon dominates, and for high n, the 5-gon dominates. So there's a phase transition between the 4 and 5-gon. The 3-gon hangs on desperately for some small n and then disappears. Okay, so that suggests, given the logic of SLT high 1, that the energy of the 5-gon phase is lower and its RLCT is higher. This is more interesting. So this is M equals 2, L equals 6. Here you can see 3-gons, 4-gons, 5-gons, 6-gons. The 4-gon phase is like participating at the beginning, but then it's this crazy dance between the 5-gon and the 6-gon. Right? So at the beginning, it's the 5-gon dominant, then the 6-gon, and then it reverses again. Now, I didn't show any picture that looked like that. Well, I didn't show any pictures that looked like any of these because I was plotting free energy, but you can imagine the pictures I was showing, take e to the minus of them. The pictures I showed had phases crossing once, right? If you think about an plus b log n, you're not going to get 2 crossings out of that. So how can we get 2 crossings? Well, there's lower order terms in the free energy expansion, right? So you see in this example, just straight away, that there's already quite interesting structure in the phases of M equals 2, L equals 6. Yeah, I can say more about this, but I think the takeaway from these plots is mostly just to convince you that this isn't some mixed up mess, right? There are very clearly phases. It's reasonable to attribute those phases to the different Kagons, and there are very clearly phase transitions in N.
Does the 4-gon pick up at the end? Is that a real thing?
I'm 10. Yeah, I don't think so. I think, I don't know where you would put it, Edmund, but I think like trusting MCMC, maybe no. So I don't think the 4-gon is coming back. Okay, so let's do a little bit of math. In order to, well, I asked the question, and this is just, we define the convex hull, count the number of points, okay? But can we find the singularity that governs these phases? To do that, we have to actually figure out what the loss function is, right? So this is in the bias, the case with bias. I'm going to dump that in a minute, so don't get too attached to this proposition. But PJK says the dot product of the jth column and the kth column is positive, and if you take it to negative, it's less than or equal to the corresponding bias. It's not symmetric, J and K. The loss function, so the toy model's potential is 1 on 3L. L is now fixed. M is arbitrary. L is arbitrary, M is arbitrary for this. This is not restricted to M equals 2. L is equal to 1 on 3LH. H is the expression you see there. It's a sum over distinct pairs of indices, then a delta function. So this term contributes to the sum if and only EJK is true. And then you get this expression, EW, some term involving only the norms and the biases. And you just do the integral. Okay, it's a bit tedious, but it's easy. Okay, so let's switch to the bias. Are there any questions about?
This is still purely in the high sparsity regime.
Oh yeah, this is all high sparsity. That's right. I don't know how to give a closed form expression for the case with sparsity. Seems nasty. Well, that's what I thought. but then Ben cried too much. So. No, he did a good job with M equals the low dimensional case. So maybe I'll try it on some other student. You seem to be moving back into my orbit after your hiking expeditions. Yes. So maybe it's for you. I'm told to hold these down.
Maybe. But it also been because you close it.
Let's see. Oh. Yeah, okay. So in the bias-free case, it's just a function of the weight matrix, right? So I'm just going to write L capital W, H capital W. Remember they were just related by a scalar, right? So I'm just going to talk about HW. And it becomes this, right? Which is clear from the previous formula. You just strip out the B's, the PJK condition, this becomes this. You don't have this term. Well, there was WJ.WK plus something cubed, but then that canceled with the prefactor. Okay, so we get this nice, simple potential. Like many potentials, it decomposes into an interaction term. Here by interaction, I mean that the optimization pressure couples two columns, right? They can't act independently. In the interaction term. The second term is a non-interacting term. It's just trying to independently make all the norms of the columns close to 1, right? So just to state out loud what's sort of clear from the formula, the optimization problem wants the columns to be unit vectors and wants all the columns to be at angles greater than or equal to pi on 2. Clearly, that's going to be tough if L is much bigger than M. So then we ask, what are the local minima, right? What are the ways of achieving the lowest possible energy? Okay, so you notice some things immediately about this expression. One is that HW is OM invariant, right? So meaning you can left multiply the weight matrix by an orthogonal matrix. That's because it's only functions of dot products, right? So the columns of W only appear in dot products with other columns. Yeah? So that's it's the one basic symmetry. The other is that it's permutation invariant. If you permute the columns, it doesn't change H. Maybe there are other interesting symmetries or local symmetries I haven't thought about. Okay, I need some notation in order to, I'm going to change coordinates a bit to tell you about the k-gons. So in general, I think it's a very interesting problem to classify the local minima. I'm just going to tell you about a very small number in 2 dimensions. Even in 3 dimensions, I think it's probably quite interesting. So this is a nice problem for somebody to think about. Here's the language in which you set up the 2-dimensional case, m equals 2. So, well, you'll notice that there's like this discrete, if you look at the formula for the potential, well, one way is thinking about it is decomposing over pairs, but really there's a natural structure on the space of weights where the same column in each chamber of this partition, the same columns contribute to the sum, right? And there's clearly potential non-analyticity at the boundary, right, where this switches from being positive to being 0. So we want to work inside those chambers. So a chamber is going to be a set, curly P, of pairs JK, distinct indices, indexes for columns. WP is going to be the subspace of the parameter space where exactly the columns, the pairs of columns in P have a positive dot product, and all the others have negative or 0 dot product. Obviously, there's a symmetry here, right? Like JK is in P if and only if KJ is in P. So you get a factor of a 2 somewhere if you ignore the order. So in the interior, it's analytic, not necessarily at the boundary. We're not going to worry too much about that. We'll just, anything I say that seems dodgy, just think about it as a limit as you approach the boundary. Okay, this isn't the time to get too fussy about that. Okay. So here's a parameterization of W that's easier to work with. Suggested obviously by the fact that all the things are dot products. Okay, so look at your weight matrix. It's permutation invariant, so you might as well assume that the columns are all in counterclockwise order, W1 through WL. Some of them might be 0, but I don't want to deal with that for now. So just assume they're all non-zero. It doesn't really make a difference. So you can basically reduce to the case where they're all non-zero. So assume they're all non-zero, order them in counterclockwise order, and label the angles as shown. So theta I is the angle from WI to WI plus 1. I can also assume all the angles are less than or equal to pi on 2. Otherwise, with a little bit of thought, you'll see that you can just reduce the problem to a simpler case. Okay. So let's look again at the potential with this parameterization. There it is in the W coordinates. If I take an index Z greater than or equal to 0, then the dot product of WI and WI plus Z plus 1, assuming they're all equal length. Okay, so I'm going to make a further restriction to all the vectors being of equal length R. In that case, the dot product is R squared. Oh, this is missing cosine squared. Oh, no, it's not squared yet. R squared cosine of the sum of the angle between them, which is just the sum of the consecutive angles. I'm only considering the only ones that show up have an angle that is less than or equal to pi on 2. Right? Okay, so I get 2. I'm summing over pairs here, so I might as well just think about the first thing in the pair and times 2, which means I'm just summing over. I look at each vector and then I sum over all the things that actually pair with it. So I sum over the i's. That means I'm looking at WI, and I'm going to look at W2 all the way up to the largest vector, which actually has this dot product positive, which means I'm looking for a Z such that theta I plus dot 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 theta I plus Z is less than pi on 2. And then I get cosine squared of the this subsequent angles. Yeah.
And to be clear, we're like wrapping around. So
that's right. Yeah, thank you. I didn't say that out loud. Yeah, all indices are read cyclically.
Yeah.
Oh, I lost the R. Yeah, thank you. Good catch. Yeah, there's an R squared here. Yep.
It should be R squared in the first.
Sorry?
Should the first line also be R squared, which is R?
So there should be an R to the 4 here.
Okay,
Yeah. Yeah, I'll get it right eventually. Right now, we all agree now it's your fault. I think it's not the 4. Okay. So by a wedge, I'm going to mean a cyclic sequence of indices which actually contributes. That is, the sum of I through I plus Z is less than pi on 2. Now, the complexity of analyzing this potential in a neighborhood of a point like this is dictated by the kinds of wedges that appear. Because, well, this is a sum over wedges, really, right? So I've rewritten H as a sum over pairs of columns to a sum over wedges. Okay, so here's the lemma, which gives you, so this is, I'm not going to prove it, it's a little Lagrange multiplier argument, nice exercise. Suppose you have a sequence of angles which satisfies these two conditions. I'll call the first one balance, which says that for any pair of columns and M, the set of all wedges. I say wedges at theta star because in a neighborhood of this parameter, nearby parameters have the same set of wedges, right? Like the definition of wedges is some condition on which sums of angles are less than pi on 2. That'll be stable to small perturbations. So nearby some fixed parameter, you have the same set of wedges. Okay, so what this says is, so J and K are fixed, and I'm going to sum over all wedges that contain J, some expression, and I'm going to sum over all wedges that contain K, some expression, and those have to always be equal. Definiteness says some matrix is negative definite. Okay, so we have both of those conditions, then any parameter whose columns are derived from that sequence of vectors with any rotation you like, it's OM invariant, of length r star is given here in a moment. That will be a strict local minimum of H. You have to understand this correctly, okay? So I've changed to coordinates that are fixed length and only parameterizing these angles. In that coordinate system, a point that satisfies these conditions will be a strict, there's an isolated local minimum of H. Now, there's no such thing as an isolated local minimum of the toy model's potential because it's OM invariant, right? As soon as you have one parameter that is a local minimum, there's a circle's worth of them at least, right? But we can factor out that, like Liam was doing in his talk. It's not an interesting symmetry. So we'll factor out the OM invariance. And so when I mean it's an isolated local minimum, I both mean like in this coordinates where I factored out the rotation invariance. And I also mean among parameters that have an equal length. So I'm not ruling out the possibility that you could wiggle these lengths in some way and achieve a lower potential. Okay, so this gives us 4, 5, 6, 7 GONs as local minima in that sense. Okay, so take theta 1 star through theta L star to be 2 pi on L. Just check the conditions. It's easy. And if you solve, you'll find that the optimal length is this expression. Okay, so that's this. I have no idea what other local minima there are even in L equals 7. But whatever they are, they don't show up in the phase plot, right? I mean, what I was showing you before wasn't some cherry-picked local minima that I actually happen to know about. It was showing k-gons. It's possible within that k-gon phase, there's like 2 very slightly different k-gons, right? So we haven't examined that closely enough. So there could be like some fine structure splitting inside these phases or something. But as I said, work in progress. We don't know whether or not that's happening. Okay, so this gives us, then you can check and say Mathematica or something, as I've done, that in the full coordinate system, these actually are critical points. Okay, so these are singularities of the toy model's potential, even in the full coordinate system. We just found them using this restriction. Any questions about k-gons? We're moving on from this detailed stuff. Okay, so reminder, this is what the phase transitions in the Bayesian posterior look like for k-gons. And 4 and 5 GONs we now know are critical points, are singularities of the potential, right? So we know the singularity that governs that phase. Yeah. Here's some more eye candy. this is showing n equals 2, L equals 6. And that's just a picture of some actual ones that you find when you so that's the Medoid centers. So this, remind me how this goes. So I'm looking at the clustering by what in order to get these pictures, Edmund?
So,
Right. So the top row are K-Medoid clustering centers. So just some way to give some labels, but the bottom row is a random selection of. So the bottom left is a random selection of everything that got classified as a 5-gon. So
Right.
has
Purple's
5 convex hulls.
Purple 5-gon.
Yep.
So this is a T-SNE embedding.
Yep.
Labeled by color, which is the F of W.
Yeah. The right, the right scatter plot is a TSNE embedding with the colors being the number of vertex in the convex hull.
Yeah, but what about the bottom right? How am I?
Yeah, so the bottom right will be the bottom right hexagon is just a random selection of the yellow point, meaning a random selection of a 6-gon vertex. It's worth noting that yes, this is a random selection, but run this many times, a random selection is always a regular 6-gon.
Actually, the structure of these clusters is probably also interesting.
The T-SNE is over weights of many independent samples. Okay.
So this is a Markov chain Monte Carlo sampler run for some number of steps. 1500, is that right?
Many more steps, but that's a column.
Right. Yeah, this is showing the distribution of this dimensionality measure that Ben was talking about, m divided by the Frobenius norm squared. There's 2 clusters showing you the 2 different phases. This is when they're in competition, right? There's the, as you can see clearly, the Markov chain is spending some time in the 6-gon phase, some time in the 5-gon phase. So this is a phase coexistence point as a function of n. So L is 6, n is what?
What? Oh, n is 7,000.
7,000, yeah. Okay, so to come back to our motivating questions, are these level sets phases associated to some singularity, which is the K-gon? Well, yes, at least for 4, 5, 6, and 7. Beyond 7, you have to start worrying about wedges with 2 things in it. And I spent literally like one night doing this calculation, so I didn't think about the case with more wedges. I don't think it's hard, but we just haven't done it. Is the change from a 4-gon to a 5-gon phase transition in some sense, right? Like, certainly yes, in the Bayesian sense. We've seen the phase plot. We've seen there's a very clear phase transition in n. But I'm saying maybe because, well, if we look at this plot against training time, the loss drops from some plateau to another plateau. There's a 4-gon changing to a 5-gon, but there's more to be said about the relationship between this picture and the phase transition in n, right? Because training time and n are not the same thing. Clearly, they're relating the two, the same sort of structure, right? Like this is the plateau, which is governed by the singularity, which is the 4-gon. That's the plateau in which sits the 5-gon. But just because the Bayesian posterior moves from one to the other, well, it does so because one has lower energy. But these two phenomena aren't instantly the same thing, right? So I say maybe we'll come back to them.
Should we think of these transition the plateaus as putting in the latent heat of formation?
Ah, good question. Yeah, ask me that question again, maybe again. Very good. Yes. At some point, right? It's not clear that there's like, I know there's this paper by Barak et al. That's talking about invisible progress measures and so on. So I think it's incorrect to look at this plateau and think there's like a secret plot from the very beginning and like stuff is brewing. At some point that starts, but it's not necessarily at the beginning. But that's right. At some point, some of the sort of entropy you're pumping out by the training process is actually going to sort of start pushing things into the other phase. Okay, so this question of how to relate a phase transition in Bayesian sense and like more microscopically, more mechanistically, is not a question that's confined to machine learning, right? This is a very normal question in science to ask. So what could be a more standard phase transition than the one we heard about in Jesse's talk involving water, right? So the phase transition from water to ice, well, still has some questions you might ask about it, right? So is it worth reading this? The intrinsic role of the interfacial structure in the melt growth of ice remains to be elucidated. That's the question we're asking, right? Like at the border of the two phases, there's like change in the structure, like crystal forms. Like the structure inside the crystal is not on my phase plot, right? Thermodynamics isn't seeing that, except insofar as like the symmetry of that crystal reflects in some higher order structure, right? But it's not like the information of what is happening to the microscopic structure, to the formation of the crystal, is all legible at the macroscopic scale in detail, right? So this is the kind of question we're now asking about the foregone to the five-gone transition. And it turns out we can say what's happening for this particular one. Okay. So let me go back to this parameterization to explain. So this is the foregone, or kind of very close to the foregone. Not writing it anywhere. I'm in the case m equals 2, L equals 5. So there's 5 columns, 5 features to be embedded. This is the local minima of the toy model's potential, which is embedding 4 features and sending the other one to 0. I'm giving these different names to the angles and so on in order that I can vary it. But there are 5 columns. This angle here, which is between W5 and W2, W1 is 0 at the foregone. I'm going to divide in half, so that's 2 theta, and then 3 psi. So 3 psi plus 2 theta is 2 pi for all these pictures. And here's a path from the foregone to the five-gone. All right. The whole time you maintain this, you maintain equal lengths for W2, W3, W4, and W5. Right? We'll call that R. And the length of this new emerging leg feature vector is S. Okay, so this is S equals 0. That's the foregone. That's S equals, well, whatever that optimal length was for the five-gone. Right? It was R star before. The optimal length of the foregone turns out to be 1. So R is 1 in this diagram, and actually something less than 1 over there. So the lengths of the other columns are also decreasing over this path. So everything's kind of changing, right? The lengths of the sort of passive vectors are decreasing slightly to reach the five-gone. This length is increasing rapidly to reach the five-gone. Well, at some point it starts increasing rapidly. That's the phase transition. But in the plateau, it's in here somewhere. Okay, that's the plateau, small l, small s. Okay, and then at the end we have theta equals psi equals 2 pi on 5.
So, I mean, some of this discreteness you see in this transition seems to be due to how you measure foregons and five-gons, because it's only measured as a five-gon when it crosses the convex hull, right?
Yeah, yeah.
So you could come up with something continuous.
Oh, sure.
That changes.
Yeah, that's not much. I don't think that's important. Yeah, but thanks. Okay, so here is so we took the toy model's potential, we factored out this 3L, and then we wrote it in these coordinates with thetas and lengths. And now we're taking a little piece of even that parameterization around the foregone and drawing a path in our minds through parameters to the five-gone. And this is what the potential looks like on that path, right? As a function of R, we're fixing these lengths to stay equal. Of course, not all lengths are equal, right? One of them is different, but we're fixing all of the others to be equal to R. The new length is S, theta. Of course, theta dictates psi by that equation. And that's if you just substitute all that into the formula we had before, that's what you get, all right? So the structure here is organized by powers of S, right? S to the 4, coefficient of S squared, which is a function of R and theta, and a constant term from the point of view of S.
What's the control here?
You're spoiling my story,
Sorry.
Jesse. Control, what's that? Spoilers, yeah. Okay, that doesn't make much sense yet. So what I want to say is that S sort of sits in one bucket and R and theta, and there's a psi there, but that's just 1/3 2 pi minus 2 theta. R and theta sit in a different bucket. Right? The reason for that has got to do with the form of these parts of the polynomial. If you look at the Hessian of this thing, it is non-degenerate in the R and theta directions, right? So in catastrophe theory, we'd call those the Morse directions. Those are the directions that are heavily constrained. And one way to see that is if you change coordinates to be at the foregone, so R star 4 means the length of those common vectors, the ones that all have the same length, is equal to that of the foregone minus R. So this is the amount by which those other passive vectors have decreased in length, right? So it starts at 0 at the foregone and it's increasing, right? Because you're shrinking the other vectors. Capital theta is the change you've made to the angle from the angle that theta had at the foregone. Okay. So that is increasing. So they're both increasing and both at 0 at the foregone. So as I said, the Hessian in these three coordinates, RS and theta, is 32, 0, 16 on 3. So that is, it's non-degenerate in the R and theta directions and degenerate in the S direction. And at the five-gon, the Hessian is non-degenerate. Okay, so that is just isolated local minima in these coordinates. Of course, it's not really isolated because the O2 symmetry, but that's sort of not important. Okay, so here we see degeneracy, right? So this is a non-degenerate singularity, non-degenerate critical point. This is a degenerate critical point. The Morse part, that is the part that belongs to the non-degenerate summands of the Hessian, is given by 32R squared plus 16 on 3 theta squared. So that's the potential that R and theta experience, right? Those are quite large numbers. So that means capital R and theta are pretty heavily constrained to be 0. That is, lowercase r and theta are pretty strongly constrained to be at their values for the foregone. Don't be fooled by this 0 here. That doesn't mean it's a flat direction. Right? The Hessian, it's an infinitesimal thing. Actually, at the foregone, there is a downward slope. This is not a local minimum. Right? It's a saddle, sort of. It's just very, very close to being 0 slope. So the negative downward direction doesn't show up until order 3, I think. Right? So it's not that this is a local minimum. It's not. There's a downward slope. It's just very, very slight. I'll show you a graph in a minute. That's the path from the foregone to the five-gon that I'm drawing. Five-gon is lower energy. I guess I didn't say that, but it came up earlier when I was showing you the phase plot. Right? Okay, so I'm going to tell you exactly the path that it takes and analyze the dynamics there, because the conclusion is kind of interesting. So we're going to take a particle. Now you might think of this as an SGD trajectory. I'm not going to treat stochasticity, so this is just gradient descent. Starting at the foregone, or very close to the foregone, it's a critical point, right? They're both critical points. So you can't start at the foregone, you'll go nowhere. So start just a little bit close to the foregone. Then the potential is H, so the dynamics are governed by dr dt is negative dH, dr, etc. Now, dH, dr, if you look at this expression, it's ddr of, I'm calling this the bifurcation term for reasons that will become apparent in a minute. That's the restoration term. That's easy to explain because that was the thing, that's the part that contributes the non-degenerate part of the Hessian. So that's the bowl that constrains R and theta. Yeah? If I take ddr of this and S is small, which it is near the foregone, this has got an S to the 4 and an S squared, and this is very small compared to these large terms. So dr dt roughly looks like not ddr of H, but ddr of the restoration term, which is minus 32. So that is to say that for small s, the evolution of r and theta is governed just by this restoration term. It's just locked into these values at the foreground. ds dt is governed by, there's no s's over there, so ds dt is just dds of what I'm calling h biff, this sum of the first two terms here. This is interesting. So that's s to the 4 plus some term that depends only on r and theta. I'm going to call that a times s squared. Now, if you're paying any attention yesterday, you already know where this is going. Okay. So when r equals theta equals 0, that's at the foregone. A is 0. I mean, that's, you know, I'm not sure that's obvious from what I've said so far. Actually, right now, sorry, just saying. You need to know the formula for r, I guess. Well, r is, no, it is obvious. Sorry, so I said r was 1 at the foregone. Theta is pi on 4, so that's 1 on root 2 squared. So that's a half of 2 minus 1. Okay, but a is 0 at the foregone. So that means that the effective potential that governs the time evolution of S, the length of this emerging feature being put into superposition, is governed by the potential S to the 4. Right? So this flat bottom bowl. I guess I said I was doing gradient descent. Now I'm changing my mind. Okay, so with a little bit of noise, or you imagine some other, I mean, there is noise because we're taking samples, right? If you look at the trajectory that I was plotting earlier, that was taking actually individual samples, right? So the curves that dropped from the foregone to the fivegone, at each step you sample one sample and take the gradient and take the step. You get the same sort of pictures if you take larger batch sizes. You're taking some samples. If you don't get any samples in this direction, the direction of the feature that's being embedded, you don't care about embedding that feature, right? So you have no gradient at all to change S, to put S into superposition. But sometimes maybe you get 10 samples in a row that are from that feature, right? In which case that will push S away from 0. And if it spends enough time away from 0, that affects the potential that govern r and theta. All right, so I said the differential equation for r and theta was given by this, but that's only true for very tiny s, right? If s acquires positive values or negative values, not meant to be clear right now what negative s should mean, it's a norm, but if it took on some positive value, then these differential equations would not be correct. The DDR, this term here, will actually contribute and effectively push r and theta away from their 0 value. So there's like this feedback effect between these two sets of parameters. So r and theta, when they're small, serve to constrain s to be near 0. But if you get enough samples that push s away from 0 and it stays there for a little while, it will change the values of r and theta. And once the values of r and theta change, the value of a will change, and it will become more negative, as you can see if you think about it. And if you decrease a, you change this effective potential for s to that one. Okay. So what that means is that the dynamics moving from the foregone to the fivegone are a cusp bifurcation, governed by control parameters r and theta and state variable s. Okay. Now I've answered your question. Did you have anything else you wanted to ask? Okay, so we've seen this picture, right? I showed you this yesterday. So moving from the foregone to the fivegone is moving down the Maxwell set of the cusp bifurcation from A, the control parameter, equals 0 to negative A.
So the foregone is at this weird like triple point?
Yeah. It's more degenerate than the fivegone. Fivegone is actually a regular point, right? In some sense, like up to the O2 symmetry.
Yeah, just repeating. So the foregone is at this triple point. So my understanding was that these triple genericity,
Triple
whatever
degeneracy, yeah.
degeneracy there, so are not that generic, or these very strong degeneracies weren't that generic or relevant, but is that right, or is it just an artifact of this
I was like-
specific toy model?
I hope I was trying to say not that.
Okay,
I mean, obviously it's a non-generic point in this parameters, but you're sort of asking why would it appear somehow? Is that,
yeah.
yeah.
I mean, does it, like, if I move to larger networks, will I have very strong degeneracy, or?
Well, you could sort of imagine, I mean, I drew these in the SLT high one, I drew these pictures where maybe over the course of the learning process, the learning coefficient increases and then it like decreases, right? So in some phases of learning, you'll actually be introducing degeneracy. So you won't always, there are paths, I mean, you can look at trajectory. Yeah, I should have said this earlier. I'm not saying that the only way to the 5-gon when you train this model is through 1, 2, 3, 4 gons. Right? You can just happen to expand all of them at once and hit the 5-gon. Right? But sometimes you hit, you're just, you know, you've got this uncontrolled fall down the loss landscape and you hit the level set for the 2-gon. When you're near the level set for the 2-gon, the gradient shrinks all the other guys to nothing. So you'll see a trajectory which starts with, because they randomly sample, they're all small and pointing higgledy-piggledy. Then it sort of happens to get into the basin, you know, the plots that Edmund was showing, right? Like you've got these local maxima, local minima, and basins of attraction. If it actually ends up in the basin of attraction for the 2-gon phase, the gradient pressure is to destroy all but 2, right? All the small ones get crushed because that's actually optimal for that part of the loss landscape. Now you're in a state where you've introduced degeneracy. So the loss landscape doesn't always go towards more generic.
Do you think this might be a more general phenomenon?
More general than what I just said.
For larger neural networks, like, should I think like these kind of?
Yeah, I think so. Yeah.
Okay.
The question is the 4-gon also on the axis straight above the triple point?
It's at the,
So
it's at the square. It's at A equals 0.
yeah, so but it's, yeah, the 4-gon is at A equal to 0.
Yeah.
I guess a related question is whether or not the path can go upwards.
Oh, it's like up to a 3-gon or something.
Oh no, this is not that question at all. The 4-gon is just at the point.
Could it go up?
Yeah.
Well, that would increase the loss in the parameterization I've chosen.
Yeah.
Yeah. So like this whole story is, there's lots of choices here, right? Like I'm choosing to take some very particular slice through the space of parameters and look at the loss on that. So not everything we're seeing is independent of my choices, right? Like some of it is like real and some of it is. Yeah? So,
So he clarified the question, what is above A equal to 0?
okay. Yes, you have to look at the formula there, right? I don't actually know. Let me think. So A is that.
You just get a.
So to make that positive, I have to make R larger, right? That would be one way of doing it. So that would be, yeah, so that would be somehow you're not at the 4-gon yet, right? Like, so like there's an optimal length for the 4-gon, which is length all 1. So if you push the lengths out, you'll be going up the loss landscape because you're not at the optimal length. You've got a 4-gon with vectors that are too long. So the gradient will push it back down to this one. That would be going up. One of the ways you can make A increase. And yeah, so maybe that would be an X squared. So that would be now a non-degenerate thing. Yeah, that's a good question. I hadn't thought about it. Okay, there are 2 local minima, right? At least for my function. A priori, my function doesn't make a lot of sense for S negative. I can make S negative in the formula, but it's parameterizing the length of the new vector, so probably can't be negative. But we're not such cowards that we can't imagine doing that. It's obvious what negative S should mean, right? Here we are at the foregon. This is growing out the leg to get to the 5-gon. That's for a positive S. That's the optimal length of the new leg over there where the system is settled. Or we can just expand the leg out in the other direction, right? That's what negative S means. This is another chamber of my parameterization, right? This is like putting the vector into a different cyclic permutation. Because I've got these columns of W, there's a different cyclic permutation that corresponds to growing it out in a different direction. And then I end up in the other local minimum. So actually S negative makes sense. And there are two choices when you grow this new leg. You go that way or you go that way. And there's two other directions, but this will do for now. Okay, so that's called symmetry breaking. That's a very typical thing that happens with a cusp catastrophe. You've got two local minima you can go to, and it's not dictated initially, right? It depends on the random fluctuations. It depends whether, I mean, the way I was saying it before, I happened to see a couple of samples of inputs that wanted me to embed feature 3, which was not currently embedded. Feature 6, let's say, was also not currently embedded. L was not specified here, but so suppose I got two features that aren't embedded and I see a lot of examples of data from about one of them, then that'll push me this way. And then as that motion accumulates, I'll end up down there. But if I'd seen samples for the other one, I might end up over here. So the symmetry is broken by the way the data is sampled. So here's a picture of what it actually looks like to move from the foregon to the 5-gon. What I'm plotting here, well, there's 3 variables, so obviously it's a bit hard to plot, but if I minimize over that energy with respect to R as a function of S and theta, so this is at the foregon, right? S is 0, theta is pi on 4. And moving down, I get to the 5-gon when S is whatever that is, 0.91, I think, and theta is 2 pi on 5. There's a couple of things I want you to notice about this picture. It's actually very flat. Right? That's what I said, right? That's to do with the fact that this is degenerate, the fact that it's an A3 singularity, it's flat. And at every point along this trajectory, like this is not a kind of cliff, right? It's actually pretty controlled. It's quadratic in the orthogonal directions to the path. So some kind of changes in the parameter will just be like, yeah, you roll down a cliff and it's just, you bounce off rocks and nothing in. There's no mathematical description of that. This is not like that. It's a very controlled transition up to a point where S is large enough that it sort of rolls down. This is a bit more exaggerated. You can see it. We transform it with e to the minus. Okay, so that's the foregon to 5-gon path. Now, what can we say based on the identification of the dynamics there? So it's well described by a second order phase transition associated with the cusp bifurcation. The other thing to notice about this is the division between control variables and state variables. That was something that emerged in the analysis, which is a polite way of saying that we made it up. But we're not completely free to choose this division between state and control variables, as I was explaining yesterday, right? It has to be appropriate in the sense that for given values of the control variables, the system kind of can be thought of as oscillating around the minimum specified by those values. Okay, and that was sort of what I was talking about when I talked about the way that R and theta were constrained and S wasn't. Notice that the state variables belong to the emerging structure in this very simple model, and the control variables were the dynamic by which the constraints of the existing structure were imposed to guide the formation of the new one. All right. So let's come back to the question of the relation between phase transitions in N of the Bayesian posterior and phase transitions in SGD steps. So let me share the sort of standard dogma in catastrophe theory of how you recognize catastrophes. Because if you have a system and you think there's a catastrophe there, there's no labeling that says these are control variables, these are state variables, this is the singularity you need to look for. You've got a lot of data, there's lots of degrees of freedom in your system. You don't know which ones to pick in order to cut down and actually find a crisp form of the bifurcation. just like we did here, right? We had to choose some particular parameterization and go to some particular spot and ignore some directions. Okay, so how do you know to start doing that? How do you know you're not just like deluding yourself to the existence of something like a catastrophe? So here are the standard answers. Modality. Near the state that you're interested in, near the sort of, in our case, the state in training, the point in training, right? You've run many SGD trajectories. They all seem to go through a similar kind of change, maybe at a similar point in training, a similar value of the loss. And you think to yourself, is there some interesting structure in the SGD landscape? Well, look nearby there for two or more qualitatively different states. For example, well, you saw in the MCMC plots that there were 5 GONs and 6 GONs both participating. That was MCMC, not SGD training. But if you look at the original paper, Ben showed this plot yesterday of, actually, I don't think he had examples against SGD time, but if you did the experiment with SGD at some point in training, you'd see sometimes 4 GONs, sometimes 5 GONs, right? Or you'd see them sort of mix near that point in training. Okay, so that's one of the so-called catastrophe flags. Sudden jumps, that's the one that's obvious, right? The loss drops. Divergence, some kind of susceptibility, kind of thermodynamics / Bayesian / statistical physics view, you'd say derivatives of the free energy, that they diverge at the same time as the other catastrophe flags. Now, in the case of the toy models paper, actually, they presented exactly such a divergence, right? They didn't call it that, but they gave this dimensionality thing that changed as they went between different level sets, right? So this is a number that changes very rapidly as you move from one level set to another. Now, you could say that's basically just looking at the loss, but it's not really, right? The Frobenius norm isn't literally the loss. It's closely related. So maybe that's like a bit borderline, but you come up with some kind of measurement. There was another custom metric in the induction heads paper, right? Rowan presented. So what they're doing is totally best practice for identifying phase transition, right? You come up with some quantity that you show characterizes these different modalities differently and which undergoes a divergence. The other thing, which is what we're sort of noticing in our example, is what you might call the plateau, right? So the plateau is an artifact of what's called critical slowing down or mode softening. Mode softening just refers to, imagine a potential, you take the Hessian, it's non-degenerate, so it's a sum of squares with some eigenvalues. Take one of those eigenvalues, tune it down to 0. That mode, when you excite it, it takes much longer to relax back to 0. Right? That's called critical slowing down or mode softening because, well, it's not rigid. Yep. Yeah, so getting stuck in a plateau is a pretty good indicator, perhaps, that there's some kind of critical slowing down. Now, depending on how you have access to the system, some of these may be easier to observe than others. There are others in the book. These are the only ones I'll go through. Hysteresis would be another example. Okay, so the more of these you see, the more confident you are that you've found a catastrophe. So I'll go back to that story related to SGD in a moment, but I want to give you some idea of, like, geometrically what it looks like to be stuck in a plateau or have a soft mode. So Mathematica failed to put the pointy tip on here, but actually this goes all the way down to the axis. That's the foregone. That's the level set, the energy level set of the foregone, right? So that's all the configurations in theta, R, and S that have the same energy as the foregone. The fact that it's a singularity, well, if you sort of follow the story with the Hessian, if locally you're non-degenerate, then a level set for the Hamiltonian is an ellipsoid, right? Because it's a sum of squares with coefficients equal to a constant. That's what this looks like, right? If you took a section of that at constant S, R and theta would be some ellipse. the radius of the ellipse becomes 0 at this level set. That's exactly because that eigenvalue has gone to 0. Okay. So the fact that you get this very pointy constrained structure in the level set is a singularity. Right? Now, what does it mean for gradient descent? So gradient descent is following the gradient of H, negative gradient. This is a larger level set, 1.001, 1. This is 0.995. The gradient is pointing in orthogonally to this surface, right? So up here somewhere, it's pointing kind of into the interior of the horn. And you can imagine if you start here, it's pretty easy, right? You're pointing into the horn, you go further into the horn, and then you just fall all the way down to the 5-gon. But down here, it's not so easy because the gradient points like into the horn. You're just stuck in the tip. That's the plateau, right? That's another way of presenting the dynamics I was analyzing roughly earlier. So that's what the singularity does. That's the soft mode. Okay. So the trajectory I was drawing is sort of slow at the beginning because it's working its way out here very, very methodically. And at some point, it manages to just roll down the hill. That's the transition. Okay, so this is the full-throated explanation of this relation N versus T now. So we have a number of runs of SGD. We observe at consistent level sets that there's a plateau followed by a sudden drop in the loss. That means we may have seen the sudden jump and critical slowing down flags. Then we look at the test loss. You can think about that as one of these quantities that's a derivative of the free energy, right? You look at local measures of complexity, maybe, like the dimensionality metric, or soon you look at rough estimates of the learning coefficient, right? If those change rapidly, you may have seen the divergence flag. If in the neighborhood of the drop, you can also identify multiple different kinds of states in coexistence, like 4-gons and 5-gons, you may have seen the modality flag, and on and on. And the more flags you see, the more confident you are that actually what you're seeing is not just like, it just happens, there's a cliff in the loss. You're actually seeing a phase transition. But note, even if you do, it's not that SGD steps is the control parameter, right? It's not how you should think of it. So once you've seen all these flags and you think, okay, probably there's a catastrophe, there's a phase transition here. By the way, I sometimes have a bad habit of using them interchangeably just to slap myself in the face. Phase transition and catastrophe are not the same thing. Phase transition is moving in the control space, right? The catastrophe is like the central governing singularity plus its unfolding. It's like the map on which the phase transition takes place, right? So the catastrophe organizes all the possible phase transitions nearby that kind of catastrophe.
What is the difference?
What is the difference between the catastrophe and the singularity?
They're basically the same thing, except the singularity is the unfolded thing. So it's like x to the 4 is the singularity. X to the 4 plus those other terms with A and B.
Right, okay.
That family is the catastrophe. Okay, so once you've identified a catastrophe, then you go looking for control and state variables, right, in order to identify which catastrophe it is. And I've done that exercise for you in the case of the toy models 4-gon to 5-gon. Ideally, then you know which catastrophe you have, and well, you hope it's on the list of elementary catastrophes, otherwise you're screwed. Will be. Okay, so supposing you succeed in doing that, then you've identified a phase transition. You're allowed to call it a phase transition then. No apologies, no scare quotes. It's associated to a catastrophe, right? Because I'm supposing you succeeded in doing that. You identified control and state parameters, and then you figure out which catastrophe it is. That means you have a catastrophe, and the catastrophe is governed by this central singularity, the most degenerate point in the family, right? That means the phase transition you spotted in SGD time has been now associated to a path in control space of that catastrophe, along which the state moves from an initial singularity to a terminal singularity. Now, here's a point where it's probably a bit confusing for me to say that, because the way I sketched it yesterday, phase transitions move from the part of the control space where you only had Morse functions to another part where you had a Morse function, right? The beginning and the end were both non-degenerate critical points, like the open parts of the control space, right? But you can move along the separatrix. Now, the separatrix isn't very interesting in the diagram I drew, but in higher dimensions, if you take like an A7 singularity, the separatrix has components of many dimensions, and there are paths where you can fall from higher dimensional parts to lower dimensional. So in our case, I'll have it in a slide in a second. Going from the foregone to the five-gone is going from the A3 singularity to just A1, right? Just a local minimum, a non-degenerate critical point. But in general, maybe it's more complicated. Okay, that initial singularity and terminal singularity are associated with phases of the Bayesian posterior. The fact that you went from W1 to W2 means that, given that SGD is probably decreasing the loss, probably E2 is less than E1 and lambda 2 is greater than lambda 1 in order for that to be, not necessarily, as I said earlier, but that's maybe the generic case. Yeah, it could have, yeah, I shouldn't have said that. This could be the other way around. So there's a phase transition of the Bayesian posterior in N, which is antecedent to the phase transition in T that you've identified. Antecedent in the sense it's like standing behind. Like the phase transition in dynamics that you saw was like a shadow of this more Platonic thing, the phase transition in N. And that's what I showed you in the foregone to the five-gone transition. So that means a very important open problem is to see if the other phase transitions that we've discussed in mechanistic interpretability have Bayesian entities in this sense. Are they organized by elementary catastrophes?
Is that a theoretical or experimental thing?
I think it's experimental first. Yeah, so you have to find it's like a two-stage thing, right? You go looking experimentally for catastrophe flags. Then the nature of the flags might give you some idea of what kind of parameters to pick. So you're probably never getting down. I mean, the analysis I did with the foregone to the five-gone is, of course, not something we expect to reproduce like that, like nuts and bolts, literally an equation, and you see a cusp. Okay, like in the induction head setting, like I'm not expecting to write down some polynomial. So this is a proof of concept for the idea. How actually to convince yourself in some more empirical way of a connection between these two things. Yeah, I don't actually have a complete answer to that. Yeah, so that's something we should figure out
Next week.
All right. So I want to end by talking about, switching gears a bit, to talk about another part of science where these ideas are one of the prevailing ways of thinking about change in structure, and that's in developmental biology. So Waddington, extremely famous, I don't know what you'd call him, embryologist, development theorist. Forgive me, I don't know the names. So in 1957, he proposed a model of the epigenetic landscape, which describes embryonic development as a ball rolling down a branching landscape. You should think of the ball as being the state of like a whole embryo, or maybe a cell or a population of cells, right? Moving on the landscape, the sort of coordinates in the plane are configurations, right? Like the expression levels of various genes, perhaps. The height is, well, it's a bit unclear what that is. But development time is moving down this landscape and making choices at each sort of stage. And these different choices, these days, we would call different cell fates, right? So like, you've got a stem cell, does it become this kind of blood cell or some other kind of cell? So Waddington proposed this as a kind of way of thinking about development. It's, obviously 1,000 times more complicated now than when he came up with the idea, and it doesn't always go one way. As you know, from stem cell therapy, you can make things go up the landscape, et cetera, et cetera. So this is quite often discussed in terms of catastrophe theory, where the branches described as cusp bifurcations. That could just be like some kind of loose analogy, but it's much more than that. So I'll show you a couple of quick slides from various papers. I'm not an expert on this literature, but I'm also not just some noob who looked at the pictures and was like, bifurcation. I took these papers to a colleague of mine, Michael Strumpf, who's head of what's the lab? It's like the genetics lab at the University of Melbourne. Yeah, he says this is legit. Okay, so, this picture? This is the critical manifold for the cusp bifurcation, right? This is them explaining it to each other. Now, this is what I really want to show you from this literature. Okay, so you might say, all well and good, you can analyze the 4-gon to the 5-gon, and maybe you can find a bifurcation, but we're talking about thousands of parameters, or tens of thousands, or hundreds of thousands of parameters. It's impossible that you're ever going to find a signal of that in the data. Not so. Okay. The biologists can do it. Are we more afraid? Okay, I don't really, actually I do understand this picture. The next one I don't really understand. This is a picture of pseudotime, which is just kind of like, biology is quite complicated when you actually try and get data out of cells, right? Because you have to do it over days and days. And so there's some kind of reconstructed development time for, there's some tens of thousands of cells involved here. And this shows you that over time, they're measuring the activation levels of certain genes by looking at the frequency of certain RNA fragments that are products of those genes. That's the gene expression data. And they can see the bifurcation in that data. Okay. I mean, this is not data. This is, if you look at the plot, not impressive. This is their simulation. So this is basically not saying anything. Really, the information is in the next slide. So over the course of development time, the concentration of various different gene products changes. And you can look for a soft mode. Okay, they detect 2. I mean, that one's very obvious. This is a slightly different metric. They detect 2, and these exactly line up with the known developmental stages in this particular kind of blood cell. Okay, and when they look at which genes are involved in this soft mode, like the control parameters, they are the genes that are involved in pathways that are known to be sort of critical in that development stage. Okay, so they're proposing, and there's a few papers. It's not large literature, I'd say. If I had to guess, I would say that there's a bit of a bad smell about catastrophe theory, as I said. So maybe like it went dormant for a while and people have just sort of started getting back into it. So maybe it's the last 5 years that people have really jumped on this idea, and the data analysis is better maybe. So don't get the impression this is like the biggest part of development biology. I'm not saying that. I honestly don't know. But these are serious papers, and they're basically doing what I'm saying with respect to looking at data and trying to infer the bifurcations, find the control variables, find the state variables, reason about the actual evolution of the system from that.
Dan, can I just ask you to clarify the word soft mode again? Or the phrase soft mode?
Soft mode. So that's like the S.
Mm-hmm.
So the S was the soft mode. That was the direction in which the Hessian became degenerate at the singularity. It's sort of stuck, right?
Mm-hmm.
Well, it's stuck, but also if you push it away, it takes a long time to come back because the restoring force is also very small, right? So if there were to be some kind of, like if you pushed it up the hill a little bit, it would slink back compared to like something acting by -32 R squared, which would come back very quickly.
Thank you.
There's a question. Did enhanced sampling shows up in the gene expression paper?
Enhanced.
Yeah,
Sorry, I don't know what that means.
neither do I.
I'd like to know this, whoever that is.
Yeah, if you can clarify, I can ask again.
Yeah, can you, hello?
Yeah, I don't think I have anything more to say about that. Oh, yeah, just a flag. This is not like 13 billion parameters and train on the whole internet big data, right? But it's bigger than one hidden layer 10H. Okay, so here's like in this language, basically what from the point of view of the Waddington landscape, this is what we're talking about in the case of m equals 2 in the toy models. Right. So let's say we're in L equals 5. So we have 5 features to assign, and we've somehow hit the level set / phase that corresponds to embedding 2 parameters, which would be put into a diagram like this. Then rolling down the last landscape, we get to make some choices about which new feature to embed. Right? Maybe we embed the 3rd column. It could have been the 4th or the 5th. And whether to embed it, I guess it doesn't make sense. Like these are all up to rotation, right? This is an O2 component. There's a circle's worth of everything. Okay, but once you hit here, there are 3 distinct choices. Well, more than that, because you could have embedded the 5th column. If you're going to embed the 4th column next, the labeling's wrong. Sorry. Pay attention to the colors, not the numbers. Sorry. You get to choose to embed it sort of in different places, right? Those are actually different components of that phase. And then when you get to the 5 gon, well, you have many other ways. So these are, sorry, that's so good, you should see it 3 times. So these are different circles sitting at the bottom of your lost landscape. Right? So you're starting up at the 2 gon, and there's many different places you can end up as you roll down. Yeah.
Do we know if each of those circles m-dimensional spheres, well, circle in this case, sorry, are they disjoint?
Yeah.
Okay, they are disjoint.
As long as the cyclic permutation is different. It is true.
Okay.
Yes.
Nathaniel clarified that enhanced sampling is a family of techniques for sampling very high dimensional probability distributions, mainly used in biological application. So
Cool.
if that showed up in the gene?
I haven't seen that term in these papers, but I probably also could have easily missed it.
Yeah.
Yeah, thanks. That's interesting. All right, so I'm going to conclude by stepping back and now talking about what this picture means for the broader agenda. Of course, that's speculative, right? This is one example and a very detailed transition in that example. I have not analyzed in this detail, even like the relation between some of the other GONs, right? So don't overestimate my level of certainty about the picture I've presented. 4 gon to 5 gon, it is as I say, but I'm not claiming to have complete knowledge of the relation between all the other GONs. But that mathematical structure is almost certainly very interesting, independently of any of the other things we're talking about. So this is a really beautiful example for models of superposition potential. So here's one way of thinking about what's happening and why, like what's happening in the plateau, like what's this process. So you can think of the combinatorial optimization problem that H is trying to solve as hierarchical, right? You can arrange the first k columns and then start to think about the remaining L minus k columns. And that might just happen randomly because you're just descending freely and you happen to hit a solution for the first k columns. Or you've solved 2 columns and then 3 and then 4 and then 5 up to k. But in any case, you've solved k. Now, the problem is not to arrange L columns, right? In some sense, the choice of how to arrange the k columns is not fixed. You could always undo it, but that would require going back up the development landscape and then down again. Very unlikely, right? So essentially, the current structure is close to fixed. Okay. So what that means is that the current structure in a given phase behaves a bit like soft architecture, right? It's like not exactly like a parameter anymore. It's kind of harder to change than the other parameters. You might think of it as more like the model architecture than a parameter. And that division is sort of the division between the control parameters and the state variables. R and theta change during the transition, right? Like R shrinks, theta increases, but much less than the state variables. And this is a relatively tiny problem. If you have a more complex neural network, maybe it's got many circuits in it, you're growing a new circuit, it's going to be very hard for that new circuit to have an opinion about how everybody else should change in order for me to do my thing, right? Much more likely it's going to evolve in the context of a relatively fixed background. Okay. So to summarize, there's a relation between phases of the Bayesian posterior, plateaus in the training process, and singularities of the potential. And a relation between phase transitions in the Bayesian posterior.
Sorry.
Yeah.
The internet cut out.
Okay.
But purpose is back, so I'll change back.
Cool. Thanks for it.
Can you let keep it on for now?
I'll leave it on.
Can you still hear me? Can someone test?
Can you check? Yep, I can hear myself.
Hello, testing?
Yep.
Okay, hi everyone. Our internet dropped out. And that's gone to some reason. Do you believe everything's good to continue?
I believe so, and if anyone in the chat don't believe so, please say so. But that's
Okay, I'll say it twice if necessary. So there's a relation between phase transitions in the Bayesian posterior.
not getting screen.
Sorry?
Can you share your screen?
Oh, thank you. Yeah. Yeah.
Yep, that works now.
What?
I can see the slides now.
All right.
Oh, there's a lag, so yes.
Okay, let me try it.
Lag. Good. Okay.
All right. I'll just start from the beginning, I think. Yeah. So to recap, there's a relation between phases of the Bayesian posterior, plateaus in the training process, and singularities of the potential, and a relation between phase transitions in the Bayesian posterior, sudden drops between plateaus that possess the catastrophe flags, and changes in the geometry of singularities, A3 to A1 in the case of foregone to fivegon. So that's moving in the control space along the, well, in this case, off the separatrix. Not all changes in the weights of a neural network occur in transitions. For example, as we've discussed several times now, you might just roll in some uncontrolled way onto the level set of a two-gon without that involving any phase transitions necessarily. But that becomes harder the more structure there is, right? The more structure there is, the more constrained the evolution is of the rest of the parameters. So potentially you could conjecture that past a certain initial stage of pretty random growth, most or perhaps all significant changes in form occur in phase transitions. And yeah, we should credit Renee Thom, who basically said much of what I'm saying here many decades ago, not about neural networks, obviously, but this is this idea about changes in form and their relation to catastrophes is the genesis of catastrophes. All right, if all that lines up, then we can think of the sequence of phases and the corresponding changes in geometry over the course of Bayesian learning, or SGD, as a kind of skeleton of a geometric program, right? Like all these phase transitions, the corresponding changes in geometry, the control parameters involved, the state variables involved, past changes influencing the control parameters for future changes, all of that together is a structure that perhaps encodes, according to this hypothesis, most of the structure that is embedded into the computational content of the final trained network. And exploring that hypothesis is the aim of developmental interpretability, which we're going to develop next week. Okay, that's it for the talk. I'll just leave you with some eye candy. Kagan proportions, that's Bayesian generalization error over there. This is the learning coefficient over training, showing some sort of curve like what I was talking about in SLT high 1. All right, thank you.
Can you calculate the LCT explicitly here, or is it there's a hat?
Oh, I knew someone was going to ask that. Yes, I can.
But you
But
haven't.
something doesn't fit. So it's like something is wrong. The experimental value, or like I think it's 9, which makes sense with this picture. But yeah,
Eventually 9.
it's eventually 9. Oh, this one's fine. Now this is 9. That's no problem. This one,
Yeah.
this one I'm sure about. What I'm talking about is the foregone when L equals 5. I think I know what the value is, but there's something a bit mysterious about these plots. So something doesn't quite match up. So I'm not going to say what I think the answer is while I could still be wrong. Yeah, but yeah, you can work it out. It's easy.
Maybe another question. Can you say anything about, supposing this becomes a mature field, what do we learn about other disciplines, about biology, about physics?
Yeah, I guess that so if you develop good tools for doing this from data, there's no reason you couldn't point the tools at this as well as at neural networks and extract some kind of map of the underlying logic of the developmental pathway. I mean, that's what they're trying to do in some sense, right? They don't have SLT, they don't have, I mean, that's maybe one thing worth saying, right? Like, okay, you can tell this story, but why is SLT really necessary here, right? You just have the idea of phase transitions, is that all? Well, no, I mean, SLT gives you a principled theoretical way of coming up with these divergences, for example, right? To find these catastrophe flags and to figure out what kind of singularities are involved, right? So and to actually be able to talk in an adult way about those measurements, like an actual statistician and not just like, I think that's kind of what's happening. To be clear, that wasn't meant, that wasn't a dig on mechanistic interpretability people, right? That was me laughing at myself looking at things. That isn't what mechanistic interpretability people are doing, right? But it would be good to be able to have decent statistics to put around to say that like a distribution of possible structures and to say this is the mean and this is the variance, right? So that's what a grown-up scientific field looks like. Yeah. There's no reason you couldn't do that kind of thing with this field. I suppose that's also a note of caution. I wouldn't say a lot of effort has been poured into this direction. If this had been a thing people had tried to do for 30 years and failed, that might give us some reason to be worried. This is a relatively new direction in developmental biology. I think we can learn a lot from what they're doing and offer something to them as well. So yeah, I think this problem of mechanistic interpretability is to some degree like a problem of understanding the emergent computational logic of learning systems writ large, right? Not all of it, but a lot of it is sort of common to many other self-organizing systems.
What might a successful developmental interp analysis of an n-ness network look like? Nathaniel asked.
Well, I mean, if you put that into just the broader context of vision networks, then presumably you would have as one of these catastrophes the formation of these different kinds of detectors, curve detector, and the circuits that relate them. That would be the obvious answer, right? Like the kind of known answer, you would see that emerge automatically by detecting the transitions in which those things form. Actually, surprising nobody's actually done that, right? Look at a small vision network. And
Come join us next week.
that's right. So much low-hanging fruit. Don't let us eat it all.
I guess I have a related question, which
Yeah.
is the role of geometry in interpreting or detecting what's going on. Like I don't think we ever mean geometry means that we know the topology of the local level sets, or we know things like that. But it's like we want sort of big broad stroke geometric quantities.
Well, in the context of what I've just been talking about, the geometry is pretty mild, right? The elementary catastrophe is very short-lived by geometry standards. I mean, they're literally called simple singularities, right?
Yeah.
So if the phase transitions belong to that class, then you just open up Gilmore's book, you look at the separatrix as a stratified topological space. That is like the way things can change. And you don't really even have to know much geometry, right? You just need to know the combinatorics of those existing catastrophes. And those books, like Gilmore's book, are meant to teach scientists and engineers to reason about those systems exactly without knowing any algebraic geometry. Right? Now, probably what's happening in singular learning theory is more complicated than what anybody has ever done with catastrophe theory. Right? So I'm not saying that we only end up with the ones on that list, or that we're not forced to understand more complex geometry. But it's not like the initial point isn't like super galaxy brained singularities necessarily. Right?
Yeah, I guess I was more commenting on the to reach the moonshot. It's not like we need to know what the surface look like in that 10 billion dimensional space, but it's more like we want to derive a geometric quantity, a quantity that depends on a geometry that is effectively computable. And to any part in geometry has algebraic geometry or geometry in general have work with that kind of 100 million dimensional space.
No, not that I know of. I mean, robotics and computational algebraic geometry have long been linked.
Right.
People are solving Grosvenor bases in relatively large number of variables in those problems, but I don't think it's hundreds, let alone thousands.
Yeah. Okay.
So I don't know that empirical algebraic geometry is a well-developed field. Until now. Now we have a reason.
I'll say that RLCT estimate will be quite, and it's an empirical geometric quantity.
Yeah, that's right.
Could you go back to the slide with the near the beginning with the experimentally sampled K-gons?
Oh yeah, sure. This one?
No, it's a bit back. It's the ones you sampled from the.
Oh, right. Yeah, I know which one you're talking about.
Yeah, it's called. Let's see, where was it? It's a bit further.
I must have gone past it, didn't I?
Closer here, yeah. Well.
Yeah, it's after this. I remember that. Yeah.
Yeah, here.
Yeah.
Let's see. Oh no, never mind. This is more in line with what I expected. I remembered a plot where you showed. I remember the plot where you showed the 5-gon, which had already parted before the new weight got to any significant length, and that was really surprising to me. Given the story you told before.
Yeah,
that's not what this looks like.
no,
This
that
makes
shouldn't
more sense.
happen. There is a
Right,
path
exactly.
where there is a path where two new vectors appear simultaneously and have the same length. Like going from like a 3-gon to a 5-gon.
Right.
And yeah, I don't know, like on the plane home, I'll think about that.
Right. No,
There's lots of, you can stare at these plots for ages and have fun trying to find
right.
what they're doing.
Yeah, no, there's no surprise here. Never mind.
Maxine say, thank you for the great talk. Do you have intuition for what family of singular learning machines would be most amenable for testing this theory in more generality?
Yeah, I guess there's two directions. One is, as we discussed yesterday, taking some of the mechanistic interpretability examples where we know there are phase transitions and structure, Another is coming up with more synthetic examples, right? I would say if like from first principles, like you just sort of know a kind of structure and then you engineer a model where you expect it to appear and you see it appear. That would be an important thing to do. A third case is starting with things that we already know have computational structure, like Turing machines or Landau-Ginzburg models, lambda calculus, Markov models. Yeah, actually, there's a paper by Zwerneck that has some RLCT calculations for such things. So that would be another good place to look. Yeah. Start with things that have algorithmic or sort of combinatorial structure, set them up in the context of SLT, and see whether the changes in structure are visible and what catastrophes they correspond to. Yeah, I expect that could keep people busy and produce a ton of beautiful papers. Yeah.
Nathaniel asked, in general, and not just in toy models, is there some kind of easy visual interpretable diagram which embeds a lot or all of the relevant phase change singularity information, something which it's like persistent diagrams and barcodes in topological
yeah, good question.
data analysis.
I don't know anything. Good project. No, I don't know anything about such tools. Yeah. I'm not sure that, I mean, this idea of actually taking seriously what Tom was putting forward as a kind of way of empirically measuring forms in the world and inferring things about them. I think very few people have actually taken that seriously as like an empirical, down-to-earth scientific enterprise versus like a high-level descriptive enterprise, which is how catastrophe theory sort of got started and maybe hit the rocks. And it's only really quite recently that papers like these biologists are sort of like, okay, let's actually try and do this, right? We have the computers, we have the data, let's see if we can find what's going on here. So I think, I mean, maybe there are other fields of science using these ideas and I'm just not aware of them. That's certainly possible. But I think the question Nathaniel's asking is a very sensible thing to have if you're taking seriously that program. I don't think people have taken it seriously. So.
And yes, it's Renee Tom.
Yeah. Any other questions here? All right. Thank you.